Welcome to Chemistry Solutions with Steve. This is a walkthrough exam paper and it's the 2019 Chemistry Higher Paper 2 and it's the single science. You can download all exam papers from the AQA website, and if you just look at the link below you can follow that straight to that site. This can be used by teachers and students. For teachers perhaps who are not specialists in science, or perhaps are science teachers but not specialists in chemistry. Students, you can use it in a variety of ways. You can print a paper copy and fill it in, stop the video at certain points, rewind, etc. You can sit the exam in one full sitting and then go back and replay, mark it yourself. The choice is yours. So we'll start with some general exam advice. You'll be given the exam and you'll be able to look at the front page and go through that front page before the examination continues. And what I suggest you do is go through each of the bullet points on the front page and you tick it when you've read it. You know, use a pencil and just tick each bit when you've read it. And that way you know that there's no information that's going to be any surprise. Another piece of equipment that you might find useful is a highlighter pen, and this will help you to highlight key words, command words, and number of marks available for each question. So I'll demonstrate this now. And we'll begin with question 1. This question is about crude oil and hydrocarbons. Figure 1 shows a fractionating column used to separate crude oil into fractions. And you'll have seen this diagram many times. It's in your textbooks and your revision guides. There's a furnace, which we'll come back to later, and some different fractions on the right hand side there. Table 1 gives information about some of the fractions, and you can see all the different fractions listed there, and the second column is the boiling point range in degrees Celsius. Question 1.1 suggests a suitable temperature for the furnace in figure 1. And this is for 1 mark. So let's go back up to the diagram and look at the furnace. The furnace's job is to turn all of the crude oil into vapours. In other words, to boil it all, to vaporise all the gases. So obviously they need to make sure that the fraction with the highest boiling point range is vaporised, and that is the one at the bottom there, bitumen, which is the 400 to 450. So to get 1 mark for this question, you write 400 to 450. 1.2. Explain why diesel oil collects above heavy fuel oil but below kerosene in the fractionating column. Use table 1, and this is for 2 marks. Now, if you look at table 1, we've highlighted kerosene, diesel oil and heavy fuel oil. Consider the diesel oil kerosene first. If you look at the temperatures, the boiling point range for the diesel oil is higher than that for kerosene. If we compare it to heavy fuel oil, we can see that it's lower than that for the heavy fuel oil. So we simply need to put this into some sort of a sentence. So let's go back to the answer space. Diesel's boiling point range is lower than the heavy fuel oils, and that's for 1 mark. Now, because it's an explain question, we need that connecting word. So we've put, but diesel oil has a higher boiling point range than kerosene. That's the second mark, 2 marks. Back of the net. 1.3. Suggest 2 reasons why bitumen is not used as a fuel, and this is for 2 marks. Let's jot down some notes here. What do we know about bitumen? Well, we know it's extremely thick, or we might in science terms call it viscous, very viscous. We should also recall that it's not very flammable either. Doesn't set fire easily, and it has a very, very high melting and boiling point. Now, these are qualities that you don't want in a fuel. You want the exact opposite. So to get 2 marks, any 2 for 2 marks. Bitumen would be too viscous, not very flammable, have too high a melting point. Page 1.4. Petrol contains many alkanes. Which of the following compounds is an alkane? Tick 1 box for 1 mark. So let's look at the generic formula for alkanes. We know that is CN H2N plus 2. So all we have to do is apply that to our 4 choices. So the first one, C2H4, 2 plus 2 is 4. That doesn't fit the formula. Next one, C4H8. That doesn't fit the formula. Now, C6H14. 2 6s are 12. Plus 2 makes 14. That does fit, so we'll give it a tick for now and do the last one just to be sure. C8H16, that doesn't fit the formula, so it's the third choice. C6H14, tick the box for 1 mark. Next question. Large hydrocarbon molecules in the diesel oil fraction are cracked to produce smaller hydrocarbon molecules. 1.5. Describe the conditions needed to crack hydrocarbon molecules from the diesel oil fraction. This is for 2 marks. Now this is a simple recall, really. You need to know what cracking is, and for cracking you need a very, very high temperature, and you possibly need a catalyst, or indeed you could use steam. So for 2 marks, in the space provided, we should write a very high temperature plus either a catalyst or the presence of steam. 1.6. Explain why large hydrocarbon molecules in the diesel oil fraction are cracked to produce smaller hydrocarbon molecules. And this is for 2 marks. Let's make some notes. Firstly, there's a high demand for small size molecules of hydrocarbons, things like petrol. An explain question, so we need a because. And these small molecules, the high demand is because they're more useful. They also flow more easily. Things like gases and petrols, they flow easily. And they are required for chemical food stock, for making other chemicals like polymers, etc. So, in order to claim 2 marks for this question, you must say there is a greater demand for small molecule hydrocarbons. That's the first mark. Second mark, this is because smaller molecules, and you can have any one of these, are more useful, make better fuels, can be used as chemical food stocks to make polymers, etc. 1.7. Complete the equation for the cracking of C5H32, and this is for 1 mark. Now, the most important part of this is that on both sides of the equation, either side of that arrow, the numbers of atoms of carbon and hydrogen must add up to be the same. So there must be on the right hand side 15 carbons and 32 hydrogens. So we can do a bit of simple maths here. There are 12 carbons on the right, so if we take that away from 15, we get 3. There are 26 hydrogens on the right. Take that away from 32 and we get 6. So on the right hand side, in the space provided, there must be 3 carbons and 6 hydrogens. So we write C3H6 for 1 mark. Question 2. This question is about lithium carbonate. Lithium carbonate is used in medicines. Figure 2 shows a tablet containing lithium carbonate. Here's figure 2. Lithium carbonate contains lithium ions and carbonate ions. A student tested the tablet for lithium ions and for carbonate ions. The student used a metal wire, dilute hydrochloric acid, lime water. Plan an investigation to show the presence of lithium ions and of carbonate ions in the tablet. You should include the results of the tests for the ions, and this is a 6-mark question. And it's also a levelled question. So let's have a look at the level descriptor. To get level 3, which you need to do for 5 to 6 marks, the design or plan would lead to the production of a valid outcome. All key steps identified and logically sequenced. So let's crack on. Now, to test for lithium ions, you would need to do what we call a flame test. You'll remember these and probably done them in class. And also for carbonate, it's a bit more tricky, but you have to add some acid, some hydrochloric acid, to get carbon dioxide, which you then test with lime water. So here's the answer for lithium ions. Crush the tablet in a mortar and pestle. Take the wire and sterilise it in concentrated hydrochloric acid and a hot Bunsen. Dip the wire into the lithium carbonate powder. Place at the top of the blue cone of a roaring Bunsen flame. And the result, you should observe a crimson colour in the flame, and that's lithium ions. For carbonate ions, place some of the lithium carbonate powder into a test tube, add some dilute hydrochloric acid, attach a tube and test tube and pass the bubbles of gas through some lime water in the second test tube. And the result is that the lime water will turn cloudy or milky, hence proving it's carbon dioxide and thus a carbonate. 6 marks. 2.2. The tablet also contains other substances. The substances in tablets are present in fixed amounts. That's a key phrase, that. What name is given to mixtures like tablets for 1 mark? And this is a simple recall, and the answer to this is, as you will know, you should know this, formulations. So for 1 mark, you must write formulations. 2.3. The tablet has a mass of 1.20 grams and contains 700 milligrams of lithium carbonate. Calculate the percentage by mass of lithium carbonate in this tablet, and this is for 3 marks. Now, if you've used your highlighter correctly, you will have noticed that the mass of the tablet is in grams and the mass of the lithium carbonate in milligrams, and we need to put these in the same units. So let's change the milligrams to grams. So a milligram is 1,000th of a gram, so 1,000th is a factor of 3, so we go 1, 2, 3, that gives us 0.700 grams of lithium. So we need to find the percentage of that in 1.20 grams. So we're going to write an expression 0.700 divided by 1.20 multiplied by 100 to take it to a percent. If we crunch that on our calculator, that comes to 58.33 recurring. Rounding up to 3 sig figs, we get 58.3. 1 mark for the final answer, 1 mark for converting milligrams to grams, and 1 mark for the percentage sum. 3 marks, back of the net. Over the page, question 3. This question is about rate of reaction. A student investigated the rate of the reaction between magnesium and dilute hydrochloric acid. The equation for the reaction is Mg bracket S plus 2HCl bracket AQ goes to MgCl2 bracket AQ plus H2 bracket G. 3.1. Which state symbol in the equation for the reaction does not represent one of the 3 states of matter? Now, this is a question asking you if you can know what all the states of matter are, but it's a sort of a reverse psychology one. So if we look through each one, we've got magnesium is a solid, that's a state of matter. AQ, don't think so, but let's check the others. AQ, don't think so. G for gaseous. So AQ for aqueous is not a state of matter, so that has to be written on the line for 1 mark, AQ. Next question. The student determined the rate of production of hydrogen gas. 3.2. What 2 pieces of measuring apparatus could the student use to find the rate of production of hydrogen gas? This is for 2 marks. If a gas is produced, we need some kind of container in which to collect it. One of the ways of doing this would be a gas syringe, but equally you could have an upturned measuring cylinder in a water bath. I'm sure you've done both of these in your school practicals. And also, when determining the rate of something, we have to work out how fast. So something needs to be timed, so we need a timer like a stopwatch. So to get 2 marks for this question, we must write in the space provided a gas syringe, upturned measuring cylinder in a water bath will do, but gas syringe is easier to write, and a stopwatch for 2 marks. Over the page now, next question. Table 2 shows the results of the investigation. Here's table 2, and you've got a column for the time, 10, 20, 30 and so on, seconds. The second column is the rate of production of gas in centimetres cubed per second, and you can see the numbers in there. We'll come back to those in a minute. Question 3.3. Plot the data from table 2 on figure 3. You should draw a line of best fit, and this is for 3 marks. This is a graph drawing exercise. So let's look at the scale. If we look at the vertical axis at the bottom here, between 0 and 1, there are 5 small marks. So those marks are each equal 0.2 centimeters cubed per second. When plotting a graph, we must make sure we get the right numbers in the right order. So we go back to the table and we tick each point as we plot it. Then we use our ruler, we work out where the first number is, 6.9. And then we move across with our pencil to 10 centimeters. You've done this many times. Then we carry on going through each plot until we get our nice sharp crosses with our very sharp pencil. Once we've done that, we draw a line of best fit, and then we've got our 3 marks. Let's have a look at the allocation of marks. There's 2 marks for getting all the points in the right place. And you've got a half a square allowance either way. And then the final mark is for the line of best fit. Over the page. 3.4. Give 3 conclusions that can be drawn about the rate of reaction between magnesium and dilute hydrochloric acid in this investigation. Use data from figure 3 and table 2, and this is for 3 marks. Now, if we go back to the graph, if we look at the first part of the graph, slope is going down from left to right. So what's happening is the rate of the reaction is getting slower. And you can see this from the graph, but also from the gas results in the above table. Then if we look at the middle part, this rate at which it's decreasing is actually slowing down because the curve is becoming flatter in its curve. And then finally, at the very end, on 60 seconds, the reaction has stopped, so the rate must be 0. If you wanted to, you could add also a little bit of detail. So, for example, the rate is decreasing more slowly around 30 seconds. So let's look at the answer grid. For the first point, the rate of reaction is decreasing or slowing down. Second point, rate is decreasing more slowly, around 30 seconds. And then finally, for the third mark, the rate is 0 at 60 seconds. 3 marks. 3.5. The student repeated the investigation using dilute hydrochloric acid at a higher temperature. All the other variables were kept the same. Which 2 statements are correct? You have to tick 2 boxes, and this is for 2 marks. Now let's look at some chemistry here. What's going on? Before we look at the choices, we know in chemistry, increasing the temperature is going to increase the collisions, so the reaction's going to go faster, so we're going to get more bubbles initially. Because we're keeping all variables the same, even though reaction is going faster, we should still get the same amount of gas. So there should be no decrease or increase in the amount of gas collected. So let's look at the choices. More bubbles were produced in the first 10 seconds. That could be a runner. Yes, so we'll give that a tick. The activation energy for the reaction was higher. Not sure about that. The magnesium was used up more quickly. Yes, that will definitely happen. The reaction that finished at the same time, well, that's the opposite of the one above, so that can't be true. The total volume of gas collected was greater, so that's not true either from the above. So, to get 2 marks for this question, we must tick the first box. More bubbles were produced in the first 10 seconds. And the third box, the magnesium was used up more quickly. Question 4. This question is about the corrosion of metals. The corrosion of iron is called rusting. 4.1. A student investigated the rusting of iron. This is the method used. 1. Set up the test tube shown in figure 4. Leave the test tubes for 1 week. Examine the nails for signs of rust. Test tube 1 shows an iron nail in water. Test tube 2 shows some dry air in the test tube with an iron nail, and a rubber stopper to keep the air dry. Test tube 3 shows the iron nail in some boiled water, which will have the air excluded, and a layer of oil on top. Test tube 4 shows a painted iron nail painted in water and air, and then test tube 5, a stainless steel nail in water exposed to air. Explain what would happen to the nails in each of the test tubes, and this is for 5 marks. So let's go back up to the diagrams. In test tube 1, the nail is exposed to air and water, so therefore it will rust. So for our first mark, tube 1, the nail will rust because, and that's underlined because this is an explain question, it is exposed to both air and water. Now, the important chemistry here is that both air and water are required for rusting to occur. So if we look at test tube 2 now, there's dry air, there's no water in test tube 2, so there'll be no rusting. So for our second mark, we should write tube 2, the nail will not rust because whilst there is air, there is no water present in the tube. So let's look at the conditions in test tube 3. In test tube 3 there is boiled water, which means the air has been excluded, so it's water only. So the nail will not rust here either. So if we go to our answer grid for tube 3, the nail will not rust because whilst there is water present, there is no air in the tube. Test tube 4. In test tube 4 there's water and air, but if you notice the iron nail is painted, and this will prevent any air or water getting to the iron. So this one will have no rust either. So for our fourth mark, tube 4, the nail will not rust because the nail is painted. So neither air nor water can come into contact with the nail. Test tube 5, similar to 4 in that there's air and water, but we haven't got an iron nail, we've got a stainless steel nail. Now stainless steel, remember, this is just iron that's been treated with some extra things and it prevents corrosion. So for the fifth and final mark, the nail will not rust because whilst there is air and water present in the tube, the stainless steel nail is resistant to corrosion. 5 marks. 4.2. Magnesium is fixed to some steel ships. Explain how this prevents the steel from rusting for 2 marks. This question is about sacrificial protection. Iron, and therefore steel, can be protected from rusting if it's in contact with a more reactive metal, such as magnesium or zinc. The more reactive metal oxidizes more readily than iron and so sacrifices itself, while the iron doesn't rust. And once the sacrificial metal has corroded away, it can be simply replaced. So to get 2 marks for this question, you must write magnesium is more reactive than iron. That's the first mark. Therefore, the magnesium offers sacrificial protection. 2 marks. 4.3. Explain why aluminium window frames do not corrode after they're made, and this is for 2 marks. Now, aluminium is a very reactive metal compared to other metals in the reactivity list, and as soon as it's formed, it forms an oxide layer, and this aluminium oxide layer offers protection for the aluminium, and so therefore it no longer corrodes. So in order to get the marks for this question, aluminium quickly forms a coating of aluminium oxide for 1 mark. It's an explain question, so we need a connective word, so this oxide layer prevents any corrosion. 2 marks. This question is about combustion of fuels. 5.1. Some central heating boilers use wood as a fuel. Suggest 2 reasons why wood is more sustainable than natural gas as a fuel for central heating boilers, and this is a 2 mark question. When we see the word sustainable, we're always thinking about renewable versus non-renewable and the effects of adding carbon dioxide to what we call the carbon footprint. Now, we should know that wood is a renewable fuel. We can grow wood in trees. Okay, so if we can grow it again, then the wood, when it's growing in a tree, soaks up carbon dioxide and therefore does not add to the carbon footprint. So for the first mark, we must write in the space provided, wood is a renewable fuel. And for the second mark, wood does not add to the carbon footprint. 2 marks, back of the net. Natural gas is mainly methane. When methane burns, it can produce both carbon monoxide and carbon dioxide. Question 5.2. Explain the process by which carbon monoxide can be produced when methane is burnt, and this is for 2 marks. Carbon dioxide, that has 2 oxygens for every 1 carbon, and for carbon monoxide it only has 1:1 oxygen to carbon, so there's less oxygen, so there's a clue. Carbon monoxide is produced when a fuel burns with not enough oxygen. So there's insufficient oxygen to make carbon dioxide, so carbon monoxide is made. And we call this incomplete combustion. So for 2 marks, if methane is burned in a limited supply of oxygen, 1 mark, then it will undergo incomplete combustion for the second mark to form carbon monoxide. 2 marks. 5.3. Balance the equation for the combustion of methane to produce carbon monoxide. And this is for 1 mark. And there's a lot of work on this just for 1 mark. But let's go through it carefully. The way to tackle this is to balance firstly the carbons, then the hydrogens, and then finally the oxygens. We write out the individual atoms in each molecule underneath as this. So as it stands, we've got 4 hydrogens on the left, so we need to double up on this water molecule to get 4 hydrogens. Doubling up the water molecule gives us our 2 oxygens, but look now, the carbon monoxide, we've got to double that as well, because we don't like single oxygens, we like even numbers, so we end up with 2 carbons there. Going over to the left, we must double our methane, so that will give us 2 carbons and 8 hydrogens. So we must quadruple our water, so we have 4 water molecules, which gives us our 8 hydrogens and 4 oxygens. So we've reached a nice point where we've got our carbons and hydrogens balanced, and let's do the oxygens. On the right hand side, we've got 6 oxygens in total. So on the left hand side, we've got an O2 molecule. So if we multiply that by 3 twos give us our 6 oxygens. And now we can put in the numbers based on the individuals below. So we get 2CH4, 3O2 gives us 2CO plus 4H2O. And as I said, that's a lot of work for 1 mark, but they all count in the end. Over the page, 5.4. Propane burns to form carbon dioxide and water. The equation for the reaction is C3H8 gaseous plus 5O2 gaseous goes to 3CO2 gaseous plus 4H2O liquid. 3.60 dm cubed or decimeters cubed carbon dioxide is produced when a sample of propane is burnt in 7.25 decimeters cubed oxygen. Calculate the volume of unreacted oxygen. Give your answer in cubic centimetres, and this is for 4 marks. So we can go to our formula triangle for this problem, and this is about the volume of 1 mole of any gas. 1 mole of any gas occupies a volume of 24 decimeters cubed. So we can construct our formula triangle as here, volume divided by 24 times n, where n is the number of moles. Let's extract from the equation the bits we need, and the bits we need are the 5O2 giving us 3CO2. That's all we need for now. What we must do is work out what the volume of oxygen would be required from the 3.6 decimeter cubed. And we can use the table method. Down the left hand side we simply put in the volume moles ratio. We start with our known 3.6 decimeters cubed of carbon dioxide, and we go down to calculate the number of moles. So using the formula triangle, we must do 3.6 divided by 24, which gives us 0.15 moles of oxygen from the data we've got. Now we need the ratio. The ratio from the equation is 3 carbon dioxide to 5 oxygen. So in order to calculate the moles of oxygen, we must multiply by 5 and divide by 3 the 0.15 mole. One tip is to leave the 0.15 on your calculator from the previous equation. It doesn't matter if you haven't, you just type it in again. And then we're going to do 0.15 times 5 divided by 3. That gives us 0.25 moles of oxygen. Now we go back to the formula triangle. We need to work out the volume of oxygen. So we cover up the vol. So we've got to multiply 24 by the number of moles. So 24 times 0.25. That gives us 6 decimeters cubed. So the volume of oxygen to produce this volume of carbon dioxide is 6 decimeters cubed. So if we go to the question, the propane was burnt in 7.25 decimeters cubed. So now we must remove the 6 litres away from the 7.25 in order to work out the unreacted. So the unreacted oxygen will be 7.25 minus 6.0, which is 1.25 decimeters cubed. Now if we look at the answer line, it wants the answer in centimeters cubed. So simply multiply this by 1000 and your final answer 1250 centimeters cubed. So you'll get 1 mark for the final answer, 1 mark for the numbers of moles, and 1 mark for working out the volume of oxygen actually used in the equation. That's a complicated one, but follow the table method, and if you're not sure, do some more examples. Question 6. Figure 5 shows a surfer on a surfboard. This is figure 5. Surfboards are made from polymers. Surfboards have a polystyrene core and an outer skin. Question 6.1. Figure 6 shows the displayed structural formula of polystyrene. Here's figure 6. Figure 7 shows an incomplete displayed structural formula of the monomer styrene. Complete figure 7, and this is for 2 marks. So, as it says in the question, figure 7 is a monomer, and a monomer must contain a double bond between 2 carbons. So let's drop that one in there, double bond between 2 carbons. The next bit can be taken from the diagram above figure 6, because what we need now is our 4 single covalent bonds between the 2 carbons and the 4 groups at each corner. So let's drop those in, 2 there, and then 2 there. So we've got 1 mark for the double bond and 1 mark for the 4 single bonds. Over the page, the outer skin of surfboards contains a polyester. 2 monomers, A and B, are needed to make the polyester. Figure 8 shows the 2 monomers. Here we've got monomer A with this OH group here and here. And then we've got monomer B with the COOH group either side. Question 6.2. Name the functional group in monomer B for 1 mark. A COOH, this is a carboxylic acid. Remember this from your revision notes. For 1 mark, we write in the space provided carboxylic acid. 6.3. Monomers A and B join together to produce a polyester and a small molecule. Name the small molecule for 1 mark. This is an example of a condensation reaction. If you look at the top here, you've got a little OH and an H there, and H and OH make H2O, water, and water is produced. So condensation polymerization requires the loss of a molecule like water. So for 1 mark, water. 6.4. Why does this type of polyester melt when it's heated? For 2 marks. This is about crosslinks. A thermosetting polymer is one that doesn't melt, and it has these crosslinks. So our polymer is one which is thermosoftening. It has no cross links. It just has weak intermolecular forces. So to get 1 mark, you must say polymers that melt when heated are called thermosoftening. They melt easily because they have no cross links. They have weak intermolecular forces. You could get away with that as well. So for 2 marks, as your answer. This is a question, 6.5, on the using of resources, the very last topic in the syllabus, using resources. 6.5, the outer skin of surfboards is a composite material, which consists of glass fibres surrounded by a polyester. Draw one line from each material to the description of that material for 2 marks. Now let's have a look at what composites are. And they're made of 2 materials, a matrix, which is a binder, and then fibres or fragments, which are called a reinforcement. We can see here on the answers we've got matrix and reinforcement. So we're going to highlight those. We've got the reinforcement and the matrix is what binds the reinforcement together. Now if we look at this example of some materials, we can see that fiberglass and carbon fibre both have fibres and both have a polymer resin. And the resin forms the matrix and the fibres form the reinforcement. So let's look to the answer grid. Polyester is going to be the matrix, and the glass fibre is going to be the reinforcement. 1 mark for each answer. 6.6. The outer skin makes the surfboard more expensive. Suggest 2 reasons why an outer skin is added to the polystyrene core for 2 marks. Now you've got some factors here. That what do you want a surfboard to be? You want it to be waterproof, you want it to be hard, you want it to be strong and tougher. But note these words are comparatives: harder, stronger, tougher. So you've got some choices here. Any 2 of those gets you 2 marks. Over the page, 7.1. When a large amount of aluminium sulfate was accidentally added to the drinking water supply at a water treatment works. 7.1. Describe a test to show that the drinking water contained aluminium ions. Give the result of the test for 3 marks. This is a question from the analysis topic, and it's about the addition of hydroxide ions to identify aluminium, calcium and magnesium ions. And you get a white precipitate, but only the aluminium hydroxide precipitate dissolves in excess sodium hydroxide, and that's how you tell the aluminium from the other 2. So for the first mark, you would add a few drops of sodium hydroxide solution to a sample of the water, and then the result would be a white precipitate will be formed, but then dissolves to form a colourless solution if you add excess sodium hydroxide solution. So 1 mark for the test, 2 marks for the result. 7.2. Describe a test to show that drinking water contained sulfate ions. Give the result of the test. So it's another analysis recall really for testing for sulfate ions. And the test is a little bit of hydrochloric acid followed by some barium chloride, and the result is a white precipitate. So for the test, for 1 mark, add a few drops of dilute hydrochloric acid followed by a few drops of barium chloride solution, and the result is white precipitate. 2 marks. 3. Plan an investigation to find the total mass of dissolved solids in a 100 cm³ sample of the drinking water. Your investigation should produce valid results for 4 marks. Now this is a required practical that many of you will have done at some point. So you take an evaporating basin and weigh it. Add the 100 cubic centimetres of the drinking water and then weigh it again. Use a Bunsen to heat the evaporating basin to evaporate the water. You're not required to mention any detail here, just maybe put it on a water bath. Then you reweigh and reheat until the mass of the what looks like empty dish is constant. In other words, all the water has been evaporated. Then you take the mass of the clean, dry evaporating basin at the start away from the final mass of the evaporating basin, and that will tell you the mass of dissolved solids. You repeat this at least 3 times to get a mean average and also eliminate any anomalies. This is a levelled question, a levelled marking scheme. So there's only 2 levels, 1 and 2. For level 2, which is your 3 to 4 marks, the design or plan would lead to the production of valid outcome. All key steps identified, logically sequenced. So let's have a look at that in writing using our notes from the left hand side. Take a clean dry evaporating basin, weigh it, record the mass in grams, add 100 cm³ to the drinking water and then reweigh the basin. Record the mass. Heat the evaporating basin on a Bunsen burner to evaporate the water and leave any solids behind. Reweigh the basin, heat and repeat until the mass is constant. Subtract the mass of the clean dry basin from the final mass of basin, the difference being the mass of the solids in the drinking water. Repeat this at least 3 times and calculate a mean, discounting any anomalies. 4 marks. Titan is a moon of the planet Saturn. Table 3 shows the percentages of gases in the atmosphere of Titan. So here's table 3, you've got the gases, nitrogen, methane, other gases, and you've got the percentage of that gas in the atmosphere. And you can see the numbers there. 8.1, some scientists think that living organisms could have evolved on Titan. Explain why these organisms could not have evolved in the same way that life is thought to have evolved on Earth. Use table 3 for 3 marks. So let's look at table 3. There's obviously a lot of nitrogen, and let's look at the other gases. We must assume that these would maybe include oxygen and carbon dioxide, but they're in a very small proportion and there's hardly, if any. So let's get some ideas down. Titan has little, if any, oxygen and little, if any, carbon dioxide. That would be our first mark. And because it's an explain, we need those connective. This means that this photosynthesis has not occurred. If it had, there'd be some carbon dioxide to make it happen or some oxygen produced. Therefore, for the third mark, no plants have evolved and neither have any oxygen-based animals. 3 marks. 2. Saturn has other moons. The other moons of Saturn have no atmosphere. Titan is warmer than the other moons of Saturn because its atmosphere contains the greenhouse gas methane. Explain how this greenhouse gas keeps Titan warmer than the other moons of Saturn. So this is a question of application. We're going to apply what we know about the greenhouse effect to Titan. So we know the greenhouse effect is all about long and shortwave radiation. Shortwave radiation comes from the sun and it passes through the methane atmosphere. And we know that. And the Earth then, in this case Titan, absorbs that radiation and gets warmer. Now, then Titan emits longer wavelength radiation in the form of infrared. As this travels up in the atmosphere, it gets absorbed by the methane and reflected back. So the effect of that is warming up the planet. So for the first mark, the methane in the atmosphere of Titan allows shortwave radiation, UV, to pass through and reach the surface. Second mark, this energy is emitted from the surface back into the atmosphere as longer wave radiation, infrared. The longer wave radiation is trapped and reflected, reflected back by the methane, therefore causing an increase in temperature on Titan. Third and final mark, bingo. 8.3. The atmosphere of Titan contains small amounts of propene. Describe a test to show that propene is an unsaturated carbon. Give the result of the test, and you've got your test and result, and it's for 2 marks. Now, this is about the bromine water test, and an unsaturated hydrocarbon has a double bond in it, and bromine reacts across that double bond. And when you add the bromine water, it becomes colourless. Do not use bromide, it's bromine, and when you're describing the test, it is not clear. Do not use the word clear, use the word colourless. So for the first mark, we add some bromine water to the propene, and for the second mark, the bromine water will turn from orange to colourless. 2 marks. Some students investigated the rate of decomposition of hydrogen peroxide. The equation for the reaction is, there it is, the catalyst for the reaction is manganese dioxide. 9.1. Describe a test to identify the gas produced in the reaction. Give the result of the test for 2 marks. If we look to the equation, we'll see that the gas is O2 with a little g. That means it's oxygen. This is a bog standard recall from the analysis topic. To test for oxygen, you insert a glowing splint into a tube of the gas, and if it's oxygen, the splint will relight or rekindle. 9.2. A student A investigated the effect of the particle size of manganese dioxide on the rate of reaction. This is the method used. Measure 25 cm cubed of 0.3 mole per decimeter cubed hydrogen peroxide solution into a conical flask. Add a spatula of the fine manganese dioxide powder to the conical flask. Measure the volume of gas produced every minute for 10 minutes. Repeat steps 1 to 3 with some coarse manganese dioxide lumps. 9.2. The method student A used did not give valid results. What 2 improvements could student A make to the method to give valid results for 2 marks? And you must tick 2 boxes. When we see valid results, what we're looking for is to make sure that variables have been controlled. So let's look down the list and see which of these choices is a variable that's trying to be controlled. Measure the increase in mass. No, that's not it. Volume of gas. No, that can't be it. Place the conical flask in a water bath at constant temperature. That gives it away, constant temperature, so that could be one. Use 0.05 moles per decimeter cubed hydrogen peroxide solution. No, that's not going to be the same, is it? Use a mass of 1 gram. Yes, this is another variable, isn't it? We're using the same mass each time, so we tick the third and the 5th box for 2 marks. Over the page, student B used a method which gave valid results, and figure 9 shows these results. We've got a graph of volume of gas in centimetres cubed against time, and we have 2 curves, one that's a curve for fine manganese dioxide powder and one for coarse lumps. 9.3. Determine the mean rate of reaction in centimetre cubed per second between 2 and 4 minutes for coarse lumps. Give your answer to 2 sig figs and use data from figure 9 for 3 marks. Your answer must be in centimetres cubed per second. So we need to determine the rate between 2 and 4 minutes. So we take a ruler and draw construction lines on 2 and 4 minutes up to the thick line, which is the coarse lumps. From where these lines intersect the thick graph line, we draw then horizontal lines to intersect on the vertical axis to get the volume of gas at 2 and 4 minutes. Take the scale, we go from 40, 42, 44, 45 for the first one. Then for the 4-minute intersect, we go 52, 46, 56. We then need to work out the difference between 56 and 45. So we do a little sum and we can see that is 11. So between 2 minutes and 4 minutes, we've produced 11 cubic centimetres of gas. And this has happened in 2 minutes. So if we move down to the answer space, the volume of gas, as we've just said, 56 take away 45 is 11. Time is 2 minutes, but look, remember, the units for the mean rate must be in centimetres cubed per second. So we convert minutes to seconds by multiplying by 60, and that gives us 120 seconds. Moving on, to calculate the mean rate, we need to divide 11 by 120. That equals 0.0916 and so on, and we're going to round that up to 2 sig figs, which will end up being 0.092. So we'll get a mark for the working out the volume, a mark for the time, and then the final mark for doing the 11 divided by 120 and getting it into sig figs. 3 marks. Bingo! 9.4. Student B repeated the experiment with coarse lumps of magnesium dioxide. Student B used the same volume of 0.2 moles per decimeter cubed hydrogen peroxide instead of 0.3 moles per decimeter cubed. Sketch on figure 9 a curve you'd expect to see. Assume that the reaction is complete after 9 minutes, and this is for 2 marks. Let's extract some important information from this question. You'll see that the question is asking you to sketch for 0.2 moles per decimeter as opposed to 0.3. So the 0.2 is clearly less concentrated, so it's going to be slower and it will finish before the 0.3 one. Now, if we analyse it further, not only is it lower in concentration, but it is 1/2 lower. 0.3 down to 0.2 is a reduction of 1/3, beg your pardon, not half. So the amount of gas that's going to be produced is only going to be 2/3, in other words, 1/3 less. So that means The maximum volume of gas is going to be on the 40 line. I've indicated it there. So we need to draw a similar shaped graph, not as steep as the other one, and finishing it on 40. Notice also that in the question it says assume that the reaction is complete after 9 minutes. So your line, the flat part of the line, it must finish there on 9 minutes. So 1 mark for the flat line, finishing at 9 minutes on 40 volume, and the second mark for the fact that the curve is not as steep as the others. 2 marks. 9.5. The rate of reaction is different when manganese dioxide is used as a fine powder rather than coarse lumps. Explain why. Your answer should be in terms of collision theory, and this is for 2 marks. Anything to do with a fine powder or the size of particles is all about surface area, and fine powder has a greater surface area. So what this means is there will be more collisions between the powder, the manganese dioxide powder, and the solution. So as we look to the answer space, the fine powder has a greater surface area than the coarse lumps. 1 mark. Therefore, remember this is an explain question, so we need a connective like therefore, there will be a greater number of collisions in the same unit of time. 2 marks. Question 10. This question is about reversible reactions and equilibrium. Hydrogen is used to produce ammonia in the Haber process. The hydrogen is made in 2 stages. Stage 1 is the reaction of methane and steam to produce carbon monoxide and hydrogen. And the equation for the reaction is CH4 plus H2O goes to CO plus 3H2. 10.1. Calculate the atom economy for the formation of hydrogen in stage 1. And you've got the relative atomic masses there. This is for 2 marks. So if you recall the equation, atom economy is the MR, the relative atomic mass, molecular mass of the desired product, divided by the relative atomic mass or molecular mass of all the reactants, and then times 100%. Our desired product is the hydrogen, the 3H2 on the right hand side. The reactant circled here, CH4 plus H2O, that's our reactants. So we work out the MR of 3H2, which is 6, 3 times 2, because each hydrogen has a mass of 1, an AR of 1. And the MR of methane plus water is 12 plus 4, carbon is 12, hydrogen is 1, plus the water, which is 2 plus 16, add all that together and you get 34 for the MR of the reactants. So now we're just going to divide 6 by 34, multiply that by 100, and we get 17.6%. 1 mark for working out the MRs, 1 mark for the sum, 2 marks. Over the page, 10.2. Explain why a low pressure is used in stage 1 and give your answer in terms of equilibrium, and this is for 2 marks. Now what we need to do is look back at our work on equilibrium and what do we know about the effect of pressure. And let's look at these notes. An increase in pressure at an equilibrium will move the reaction, or the equilibrium will shift to the side of the equation with the least or fewest number of gaseous molecules. So let's look at and summarise that. High pressure equilibrium shifts to the side of the fewer molecules, so the opposite must be true. Low pressure will shift the equilibrium to the side with more molecules. So let's look at our equation. If we look at our equation, we can see clearly that on the left-hand side of the equilibrium there are 2 molecules, 1 of each methane and water. And on the right-hand side there are 4, 1 carbon monoxide and 3 hydrogen. So this means a lower pressure will shift to the side with the most or the highest number of molecules. So the equilibrium is going to shift right. So back to the answer space. Low pressure is used to gain a higher yield of hydrogen because we're going to get more of it moving to the right. That's your first mark. And because it's an explain, you know what I'm going to say, we need one of those connectors. This is because if low pressure is applied, the equilibrium shifts to the side with the greater number of molecules, i.e. the right. And that's your second mark. 3. Stage 2 uses carbon monoxide produced in stage 1. The carbon monoxide is reacted with more steam to produce carbon dioxide and more hydrogen. The equation for the reaction is, in stage 2, CO gas plus H2O is in equilibrium with CO2 plus H2O. What is the effect of increasing the pressure on the equilibrium yield of hydrogen in stage 2? So as soon as we see reference to pressure, we know this is about the number of molecules in the equation. If we look at the equation, we can see on the left-hand side there are 2 molecules, one of each, and likewise on the right-hand side there are 2 molecules. So if there is no difference in the numbers of molecules, then the pressure, whether it's increased or decreased, will have no effect. So to get 1 mark, we must write in the space provided, this will have no effect on the yield. Over the page, figure 10 shows the percentage yield of ammonia produced at different temperatures and pressures in the Haber process. And here's figure 10. You might have seen this before in your notes. Percentage on the left, pressure on the right. And you've got 3 on the bottom, 3 temperatures, and you've got 3 graphs representing 3 temperatures. Temperature of 450 Celsius and pressure of 200 atmospheres is what's used in the Haber process traditionally. Question 10.4. A student suggested that a temperature of 350 degrees and a pressure of 285 atmospheres could be used instead of those used traditionally in the Haber process. Determine how many times greater the percentage yield of ammonia obtained would be, and use figure 10, and this is for 3 marks. So let's go back to the graph and look at the traditional 450 degrees Celsius and get our ruler and draw a construction line up to the 450 line from 200 atmospheres on the X scale. Where our construction line meets, we draw then a line across to the percentage graph and work out the percentage. You can see here it works out at 28% yield. Now I've indicated this in red, so look at the 350 line now. We repeat this construction line up to the 350 from 285 atmospheres. Mark across to the percentage line, and you can see clearly 63% using the scale. So what the student has suggested was 63%, and what the Haber process is 28. So now we've got to work out how many more times greater the one is to the other. So we simply divide 63 by 28, and then we crunch that in our calculator, and we can see that we end up with 2.5 times greater. So the student's idea would, 2.25 times greater. So we'd get 1 mark for working out each of the 2 percentages from the graph, and then our final mark for the final answer, 3 marks. Page 10.5. A pressure of 285 atmospheres is not used in the Haber process. Give 1 reason why for 1 mark, and there are a number of reasons. Usually it's to do with energy, the equipment needed to have a high pressure, and safety issues. So you could put down here on the answer grid, the energy costs would be excessive, there would be safety issues at high pressures, or the equipment would need to be quite strong and robust and therefore more costly. Any 1 from 3. 10.6. How does figure 10 show that the forward reaction in the Haber process is exothermic? And this is for 1 mark. Look at the temperatures on the graph. At the top, 350 is a low temperature and giving a higher yield. 450 is a higher temperature and it's giving a much lower yield. This is because if the temperature is increased, the equilibrium will always move in the endothermic reaction. So the forward reaction must be exothermic because the yield is lower. So to get 1 mark for this question, we must write when the temperature is higher, the yield is lower. So now to the final question, 10.7. World production of ammonia is now about 30 times greater than it was in 1950. Suggests why the demand for ammonia has increased. And this is for 2 marks. These questions usually involve anything to do with the world stuff is usually down to population growth. So the greater the population, the greater the demand for stuff, and ammonia is used to make fertilizer and other goods. So to get our 2 marks, world population has got bigger since 1950, so this means there will be a greater demand for products made from ammonia, for example, fertilizer. So we get 1 mark for saying the world population has got bigger, and then the second mark is about the demand for goods like ammonia.